Three, two, one. All right. I'm ready. I'm ready. I'm ready. All right. So today we will see how we can apply all of the exciting knowledge we've learned about second-order differential equations to mathematical models. So specifically, we're going to look at the all-time number one Duke of New York classic, the mass spring system. All right. Okay. So specifically, we're going to focus in on one particular case, which will be the situation of free undamped motion. Your book goes through the damped motion and the driven motion cases. We'll just look at the one. If you're interested, you can look at the others. But yeah. Now, before we get going, let's agree. Let's agree. We're going to lock some assumptions down. We're going to get some operating assumptions, right? Because we're going to be doing some mathematical modeling, which means that we're going to need to make decisions. And we need to make these to make the mathematics easier. Okay. So, everything's going to be oriented vertically, where downward movement is positive and upward movement is negative. So basically, we're going to look at mass springs. So imagine in your mind's eye, we have a spring attached to a ceiling, and at the bottom of the spring is a mass. So if the mass is moving downward, we're going to consider that positive. And if the mass is going upward, we'll consider that negative. Right? If you swap it, where upward is positive and downward is negative, everything we do is fine. You just need to keep in mind, right? We just need to we need a frame of reference, right? We just need to make a decision. And the way I like it is moving towards the planet is positive. And moving up, you're working against gravity, so that should be negative, right? At least that's how I like it. If you orient it the other way, who cares? But that's how we're going to do it. Okay. And the other thing that we want to stress is that this is all taking place in physics heaven. So, everything is fine, and the only thing that matters are the things that we say that matters. Obviously, if this was a real-world situation, you had a spring attached to a mass, and you wanted to model its motion, right? You got to account for the fact of, like, how rusty the spring is, or how oddly shaped your mass might be. You're observing it moving, which is, affecting it. So, right, there's a lot of things that you would need to include, but we're going to keep things nice and clean, and we're not going to go nuts. Okay. So that being said, let's get going. All right. So we're talking about mass springs. So the first thing we want to talk about is, well, how do springs work? Okay. So Hooke's law tells us what to do. So Hooke's law says that if we're talking about a spring, okay, so a spring wants to just chill, right? It just wants to exist in its current state, and it doesn't like being compressed, and it doesn't like being elongated. Okay. Right, because if you try compressing it or you try elongating it, it's going to fight back and try to get back to normal. Right? So if you've ever taken a spring and messed around with it, you know this is true. Okay. So Hooke says that, well, the force the spring is going to enact to get back to its natural state is proportional to how much you're messing with it. So the restoring force opposite the direction of elongating the spring, so whether you compress it or stretch it, is proportional to the amount that you're doing. That makes sense. Seems pretty reasonable. Pretty solid model. Okay. So, in other words, the equation then, the restoring force opposite, if you're compressing or stretching it, should be negative, opposite, right? Where proportional, so a multiple of the amount of elongation S. So here K is what we call the spring constant, and the units on the spring constant need to be pounds per foot or newtons per meter, depending on what's going on, right? So the force, the units that we're going to use are either going to be pounds or newtons, and the elongation, the distance, we're going to stick to feet or meters. And now it's worth stressing that because if somebody wants to get a little salty on you, they won't tell you it in feet. They'll tell you it in inches, or they'll tell you it in nanometers or something. So, worth keeping that in mind. Pay attention to units. We're doing mathematical modeling. Units matter, so keep them there. But anyway, it's pretty reasonable assumption here of this is how a spring should operate. So let's check it out. All right, so suppose that a 20-pound mass stretches a spring 6 inches. Okay. So we've been told some stuff. So again, in your mind's eye, spring is attached to the ceiling. A mass has been placed on it. And it stretches it. It pulls it down. Positive amount, pulling it down 6 inches. Okay. So the restoring force then is -20, right? The negative sign because upward movement is negative, right? The mass is pulling it down, so the restoring force, which is working against it, has to be -20, right? 20 pounds is pulling it down, so a restoring force of -20 is acting against it. The elongation is 1/2, right? No, it's a stretch, not a compress, so it's positive S. Positive is down. Now note, I converted it to feet. I was given the information in inches. Be careful. People try to trick you. Pay attention to the units. Units matter. Okay. So now I can solve for the spring constant. Hooke's law tells me that the force, which is -20, needs to coincide with -k times the amount of elongation. Well, I know what F was equal to, I know what S was equal to. I can solve for K. It's 40 pounds per foot. Note the spring constant will always be a positive quantity, right? Because the opposite of the direction has already been enforced with the minus sign right there. So K will always be a positive quantity. All right, cool. So there you go. That's a pretty quick rundown of how springs should behave. The classic Hooke's law. So now what we're going to want to do is attach a mass to that spring and really get into it. So let's talk about motion. All right, because we're going to attach a mass to a spring, we're going to have it move, and we're going to want to model it. So what comes to help us? Well, it's Newton's second law of motion, which states that the sum of all forces on an object needs to equal the mass of the object multiplied by its acceleration. Now, you may have heard of this before, but you may have never actually really processed it, that he's telling you a differential equation, right? Acceleration is the second derivative. All right. So we're now going to attach the mass to the spring, and we're going to put it in the motion, and we're going to want to model it. Okay. So the first thing we should do is consider the optimal case, which would mean nothing is happening. There is no motion, right? If nothing's happening, then nothing's happening, and it's pretty easy to figure out what's going on, right? It's just sitting there. It's not doing anything. Okay, so suppose that we've got a mass. It's got a weight W. It's attached to a spring. Now remember, weight is not mass. Weight is a force, right? Weight is, right, so your weight, when you step on a scale, you get some pounds. That's not telling you your mass. That's telling you how mass and gravity are affecting things. So that's your mass times gravity is your weight. Weight is a force. It's not a unit of measurement. It's a force. It's measurement times the acceleration. Okay. So suppose we do have a mass attached with weight W attached to a spring, and no motion is occurring. They're just sitting there. Nothing's happening. Okay. This is called the equilibrium position. Right, and that's the only possible situation. So basically, the mass and the spring are attached to each other. They're hanging from the ceiling. They're not moving, so they are in harmony. They have reached equilibrium. They are fully at peace. So what's going on then? Okay. Well, there's no motion, so that means there's no acceleration. That means the sum of the weight of the mass and the restoring force of the spring, that summation needs to equal 0. Right, when they add up, there's no motion, well, there's no acceleration. Right, if there was acceleration, there'd be motion. So that means the weight of the mass, which, again, as I noted, is the amount of mass times the gravitational constant, plus the restoring force of the spring, which by Hooke's law we know is -ks, where k is the spring constant, and s is the elongation to the equilibrium position, that adds up to 0. Okay, so again, we want to stress here, all of these constants that show up are all positive. And note that for any mass spring system we'll ever create, this feature is always going to be present. It always needs to be that mg minus ks is equal to 0. Even if we were in motion, this fact is always true, right? S is the elongation to the equilibrium position, right? Where if the mass was attached to the spring, hanging from the ceiling, and no motion was occurring, this equilibrium, this harmonic situation, needs to equal 0. So mg needs to be ks, right? So the restoring force and the weight needed to line up with each other. Okay. Now I want to note something about the gravitational constant. Two possibilities: 9.81 meters per second squared. That's if the weight we were given was in terms of newtons. We would use the meter square per one. If the weight we're given is in terms of pounds, then we use the feet per second squared. Note the feet per second squared, we'll just round that to 32. It's like 32.0 something, so whatever. So, fun fact, the gravitational constant, even though it is a constant, is actually not constant on the planet Earth. It depends on where you are, what the number is going to be. The college I went to, Clarkson, the physics department, went out of their way to figure out what the explicit gravitational constant was at Clarkson University, so locally speaking on the campus. If I remember right, the gravitational constant was a little bit stronger. It was like 9.83 or something like that. So when it came to like exams, they didn't use 9.81, they used 9.83. They were like, no, that's the actual gravitational constant right here. So that's what we're going to use. So it's pretty funny. But anyway, I don't know if the physics department has used on a similar thing, but maybe they have. But all right. So yeah, I want to stress all these are positive constants, and these are an explicit feature of the system that is always present. Okay. All right, that being said, this is the trivial case where no motion is happening, so let's get moving. Okay. So let's let x of t represent the displacement of the mass then as a function of t. Time t, where time will be whatever units they need to be, and for us, because of the gravitational constants, we'll stick with seconds. Okay, so now let's note some things that are built into all of our assumptions here. So the displacement, we're going to agree that x equals 0 is the equilibrium. So if there was absolutely no motion going on and the mass and the spring were in harmony, x of 0 is where that is, whatever that location needs to be. And remember, we have oriented things so downward is positive. So if I'm below the equilibrium, so if I'm being if the spring is being stretched, that is a positive situation, right? So positive is down, up is negative. So when we're above equilibrium, x is negative, right? Compressed spring in that case. Okay. So recall, our assumptions are built in. Assuming that, it's always good to keep this in mind. Helps us out when we're solving problems. And now note something: the restoring force of the spring now is going to be slightly different, because it is going to be the equilibrium elongation, so if the mass and the spring were sitting in harmony and not moving, S. But now, the restoring force will be that plus wherever we are in the displacement. And now note, when x is equal to 0, we are at harmony, we're at the equilibrium position. Right. So the restoring force of the spring is a little bit more involved now. So Newton's second law gets a lot more spicy. Right, so mass times the acceleration needs to equal the sum of all of the forces. We are only assuming that the restoring force of the spring and the force of gravity pulling down on the mass, so the weight of the mass, are the only two things involved here. So that means we've got mass times the acceleration of the mass, which is the second derivative of x of t, the weight of the mass, mg, right there, plus the restoring force of the spring, negative ks plus x. Note, mg minus ks, a feature present in any mass spring system. We know something about that. We know that that has to equal 0, and so the movement of a mass spring system is this beautiful second order, constant coefficient, linear, homogeneous differential equation. And hey, we know how to solve those. All right. So there we go. There's the equation that governs free, undamped mass spring motion. Okay, where m is the amount of mass and k is the constant associated with the spring, hence the name mass spring. Okay, and x representing the current location of the spring, where x equals 0 is the equilibrium position, where if there was no motion, the mass and spring would be sitting in harmony with each other. All right, so we know how to solve this, right? Remember, m and k are positive constants, so we can just solve this. So the first thing we want to do is divide out by m, and for reasons, take the square root of k divided by m. Note we can do that, and it's a positive real number, because, again, k and m are features of the system that are all positive quantities. So the differential equation then turns into this one, the second derivative of x plus omega squared times x equaling 0. As we're going to see, this is the much better form. Note that if you were solving a problem, you need to be working this out. We'll see that in a moment when we work out an actual problem. Where omega is called the angular frequency. I wonder why it's called that. I bet we'll find out soon. The reason we're doing that, as you can see right now, is that it makes the general solution look a hell of a lot nicer. Because the auxiliary equation then is r squared plus omega squared, which means that r is plus or minus I omega. And so the general solution is then c1 cosine omega t plus c2 sine omega t. So, very good reason for introducing this omega. Just makes the math look a little bit easier. It does mean there's more junk we need to keep track of. But note that we went from having an equation with two constants we had to deal with into an equation with just one constant you had to deal with. And this is a thing you do all the time in mathematical modeling, where you're trying to eliminate as many parameters as possible. It's part of a broader topic known as non-dimensionalization, where you're basically just trying to make your equation as simple as humanly possible by making all sorts of assumptions. We're not going to get into that, but if you're interested, check out The Exciting World of Mathematical Modeling and all that other good stuff. Alright, so we've got the general solution, so is that it? Well, this motion, this equation, right, this is telling us how the motion of the mass is behaving. It's usually referred to as simple harmonic motion because we're free and we're undamped. And again, that's the only case we're going to look at. The other cases, the book goes from, if you're interested, check them out. But anyway, we can do a lot better than this equation, right? Now, note that if I had some initial information, like the initial position and the derivative, and information about the derivative at the initial time, so if an initial value problem, we can solve for C1 and T2, and that'd be it. But there is a much better equation that communicates all of the physical aspects of the system. So let's talk about how we can do that. So we're going to introduce two things. We're going to introduce two quantities, an A and a phi. And we're going to go ahead and say, let A and phi satisfy the following. A times sine of phi is C1, and A times cosine of phi is C2. Okay. And again, just like omega, at first it's going to be, all right, why are we introducing this? Well, note that the A quantity coincides with C1 squared plus C2 squared, so that's something, I guess. That tells me something. But the real power is plugging this into the general solution. Right, C1, if you replace it with A sine phi, and C2, there should be a plus sign. I swear to God. Swear to Jesus every time, man. Alright. So, we get this. The plus sign right there. So we replace the C2 with A cosine phi. Now, you may not notice it, but your brain does. There's a trig identity that helps us out here. And in fact, the trig identity you can derive using Euler's formula. So there's a fun fact. So as you hopefully know, there are formulas for sine of x plus y and cosine of x plus y. The way they're derived, you have to draw like a triangle, and you gotta be really clever. It's a right triangle. Let me rephrase that. It's a rectangle that you stuff a bunch of right triangles inside of, and you just gotta label everything correctly to get the formula. Euler's formula immediately gives it to you, so... Anyway, here we see it making an appearance. So this tells me now that the equation of the motion, rather than being a cosine plus a sine scaled together, is a scalar multiple of a shifted sine curve, right? Remember, x is a function of t. Omega, phi, and a are all numbers, and now, in this form, they're all numbers that have explicit information about the physical system. So specifically, a is the amplitude. This is the furthest displacement the mass achieves, right? Sine cycles through the values of -1 and 1. It oscillates between those two. So this now tells me the a here, that tells me how far away I ever get from equilibrium. So the biggest positive displacement and also the biggest negative displacement. So the maximum displacement away and the minimum displacement away. I now immediately know what that is, right? If I have the form of the motion as this equation, I can now tell you how far away from equilibrium are we ever going to be, right? It's going to be a or negative a. So the furthest stretching and the furthest compressing that the mass spring obtains. Nice. Now phi, which is called the phase angle, tells us something also about how the motion behaves, right? Because it's a shifted sine curve, the phase angle tells me that when I'm thinking about this thing's motion, right, it's going to be oscillating, so it's a sine curve, so it's oscillating like sine. Phi tells me where on the sine curve we begin. So phi would tell us, are we immediately going to move down? Are we immediately going to move up? And it tells me how far away am I from reaching a peak or a valley. All right, so having the phase angle right away tells me where things begin, and as the motion goes on, what we can expect to see first, a peak or a valley, or maybe equilibrium. And as we noted, we called omega the angular frequency, and now we see why. Well, it's scaling t, so the phi just shifts the sine curve. The omega, though, is multiplying the input. So that means this is telling us how quickly are we going to be oscillating through sine, right? Sine is an oscillatory function. Now, if omega was 2, let's say, well, that's sine of 2t, so I'm running through the inputs twice as fast, so I'm oscillating twice as fast. So this actually tells us how quickly we should expect to see the oscillations of the system. If omega is really big, it's going to oscillate super fast. If omega is really small, now note, omega will always be positive, so if omega is a really small number, well, then it's going to oscillate nice and slowly. All right. So this formula, although the machinery and the ins and outs of how we got there might be a little like artificial or maybe a little mathematically unsettling, upsetting, like you ate some math and you got some math and something, that wasn't some good math, was it? It is much better because it immediately communicates to us a whole bunch of information about how the mass spring system behaves. Alright, well, we're 7 slides deep in, we haven't even done anything, right? Let's actually solve a problem about a mass spring system. Okay. So, boom, here we go. I've got a mass. It weighs 32 pounds. It stretches the spring 2 feet. I want the equation for the motion if I further know that the mass is released 1 foot above its equilibrium with an upward force of 4 feet per second. Okay. So pay attention to all the units that we've been given. So we have pounds and feet, so we're good, we're happy, we like those. If we were told things in inches, we need to convert to feet. If we didn't have pounds, if we had like stone or something, what is that, 13 pounds is the stone? 16 pounds? I don't remember. But anyway, if you got some goofy units, we'll convert everything over. Now note, if we were given pounds, we were given newtons, we'd also be happy with that. But we wouldn't be happy with feet, we'd want meters. But anyway. Now we have all this information, what do we need? Alright, well, we want to get the equation for the motion. And as we noted, well, we need some information. Right? I need the amplitude, I need the omega, and I need the phi. So how do I figure all that fun stuff out? Alright, well, the first thing to note is that we're told the weight of the mass, W, which is 32 pounds. The units that we see going on here, right, feet and seconds, tells us that the gravitational constant is going to be 32 feet per second squared. if we're really paying attention to that. So that means the amount of mass that we have is the weight divided by the gravitational constant. So in this case, 32 over 32, that's nice, it's just equal to 1. Oh boy, it was like somebody rigged this problem so the numbers wouldn't be stupid. And it's also worth noting here that the units for this is called slugs. So, right, we use pounds to measure our weight. So, the amount of mass that we have, if you want to know how much mass we have, take your weight and divide it by 32. That tells you how many slugs you're made of. I am about 6 slugs, if you're interested. I didn't realize I had that many slugs in me, but, yeah, about 6 slugs. Okay, so what about the other information? Well, I now know the amount of mass we have, which is 1. I also now need to know what the spring constant is, so, well, we already know how to solve for spring constants. The information we were given, the equilibrium, 2 feet. So we plug that in for our elongation S. The pounds, negative 32, the restoring force of the spring. And then so we solve for the spring constant, which is equal to 16. Okay, so we have the mass, which is 1, and the spring constant, which is 16, so I can now compute the angular frequency. So, specifically remember, the angular frequency is the square root of the spring constant divided by the mass. So that's 16 over 1, square root of that is 4. So the general solution then is C1 cosine 4t plus C2 sine 4t. So we've got one of the numbers down the angular frequency, but we now need to figure out the amplitude and the phase angle. Okay, and now that's where the initial conditions are going to come in. So initially we were told we were a foot above equilibrium, and we were given a upward force of 4. And here's the next typo for the day, because right, upward force. Upward is negative. Oh, geez, that did all sorts of stuff right there. Yeah, upward is negative force, so that's right there. Fixed it. So we're a foot above equilibrium with an upward force of 4. So we're negative 1 and negative 4. Now, given these initial conditions, we can solve for C1 and C2. Okay, and you see here, I have the negative 4 right here. I just didn't have it. Whatever, man. Anyway, alright, so now we can solve for C1 and C2. There we go. So now, equipped with C1 and C2, we can solve for the amplitude and the phase angle and get the preferred formula for the simple harmonic motion. Okay, so the amplitude is easy to find. A squared is C1 squared plus C2 squared. Well, that's 1 plus 1, that's 2, so A is the square root of 2. Okay, so the amplitude is always super easy and really straightforward. You literally just figure out what C1 and C2 are from the initial conditions, and square them, add them up, and take the square root, and you get the amplitude. The phase angle, though, let me tell you about the phase angle. I've been wanting to talk to you about the phase angle all day. The phase angle is a lot more subtle and requires you to be really careful. So the information that I know about the phase angle is that the amplitude times sine of the phase angle is C1, and the amplitude times cosine of the phase angle is C2. Okay, now in this case, C1 and C2 are the same, so it well works out pretty nicely. So I have that sine of phi is negative 1 over root 2, and cosine of phi is negative 1 over root 2. Okay, leave it in this form. Your textbook, and every differential equations textbook in the universe, tells you to now look at sine of phi over cosine of phi, make a tangent of phi, and then solve for phi that way. Never do this. Do not do this. Tell people who do this that they are wrong. Write your congressman, write your senator, write the publishers, tell everyone. This is not how you should do it. Right? I absolutely hate this so much, because if you leave it like this, you have information about sine, you have information about cosine. I have told you so much information here. If I tell you tangent of an angle, I've told you less information. Right? So basically you have information, and if you go to the tangent, you deliberately removed information. It's so frustrating. Don't do that. Keep it like this, right? Because what have I told you here? My phase angle, my mystery angle, sine is negative and cosine is negative. Remember, cosine and sine correspond to the coordinates on the unit circle. The x-coordinate is cosine, the y-coordinate is sine. X is negative, sine is negative. I am in the third quadrant. I immediately know this information. So I already know how to start drawing my reference triangles, right, and using 45, 45, or 30, 60, 90 triangles to figure out what the angle needs to be. And if I can't use those, well, then I can use some arc-trig maneuvers, but I know that I'm in the third quadrant, so I know which arc-trig maneuvers to use. So the angle's in the third quadrant, and specifically sine and cosine have to equal each other, which means I need the angle in the third quadrant where that happens, which is 5 pi over 4. Never, 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 never use arctangent to find the phase angle. Arctangent sucks. Fight me, Butler. Arctangent, remember arctangent, it's got a horizontal and a vertical asymptote. Right. And what are they? Pi over 2 and minus pi over 2. Arctangent can only ever handle angles that live between the first and the fourth quadrant. If you were ever in the second and the third quadrant, arctangent is complete and utter garbage. So arctangent is only good for half of the plane. It sucks. Right? Arcsine and cosine aren't any better. They also only work for half of the plane as well, but never use them. We know what sine and cosine are in terms of the unit circle. Always go back to the unit circle when it comes to trig. The unit circle is literally everything when it comes to trig, right? Just draw it out on the unit circle and you will succeed, right? Every single goddamn math textbook just turns us into a tangent and it immediately screws everything up, right? So note specifically, this example that I used is in the third quadrant. So if you arctan this, you wouldn't have gotten 5 pi over 4. What would it have told you? It would have given you pi over 4, right? Because if you divided these out, you would have gotten positive 1. Yeah. So, all right. Anyway, so now that I'm done and I'm off my soapbox, we now have the equation for the motion of the mass spring system. It's square root of 2 sine of 4t plus 5 pi over 4. That's it. There we go. We got it. Now, that'd be good and all. And we can walk away from this if we want to. But there's, again, a lot of information that is being communicated to me from this equation. So not only do I have the amplitude, square root of 2, I now know the furthest away from equilibrium I ever get is root 2 and minus root 2. I have the phase angle, 5 pi over 4, so I know that when we start drawing up the curve, we're at 5 pi over 4 on sine's curve. Right, and then that is just going to move forward. So we're in the third quadrant, then we'll move our way into the fourth and the first. And if we think about sine, it means we're going to be decreasing until we bottom out to -1, and then we'll start increasing our way back up to 0, and then up to 1 on the sine curve. And we have 4 times t, so I know I'm going up 4 times faster than normal. So we're oscillating 4 times faster than sine normally does. So there we go. There's actually a whole host of things that this equation now tells me about the behavior of the motion. So let's unpack that. So specifically, I'm going to attack 2 separate problems. I'm going to attack the problem of after release, when does the mass reach the equilibrium position? So remember, the setup was that we took the mass, we compressed the spring so that we were above equilibrium a foot, and then we not only did we just compress it up by a foot, we gave it an initial push up. So we compressed it, we got it to a foot above equilibrium, and then we tossed it up with a force of 4 feet per second. All right, so gave it an upward velocity. So we compressed and then we pushed it up as we let it go to let it proceed to move. So we want to ask then, well, okay, it's going to go. It starts at a foot above. It's pushed up 1. Well, right, we know the system oscillates, so eventually it gets back to equilibrium. So when does that happen after the release? And furthermore, when did it reach the minimum displacement? So we know that the displacement will oscillate between -2 and negative square root 2 and positive square root 2. When does it first hit that minimum displacement? Right. So if we think about the physics of the problem, before we even get answers here, we already have an idea what the answer should be. Right? Because we pushed it up and then we threw it up. So we should hit the minimum displacement first before we come back and hit the equilibrium position. All right. So that being said, let's go ahead and solve these. So again, equilibrium, remember, corresponds to when x is equal to 0. Now, as we noted, the x here is equal to 0, but that's not where things are in reality. So remember, the equilibrium corresponds to 2 feet from the spring's starting point, right, when they're sitting in equilibrium. So if we do say x is equal to 0, that does not mean, like, position 0, right? There's a frame of reference that we've moved around to line up with the equilibrium. But anyway, just something to keep in mind while we're doing this stuff. So x is equal to 0, and I want to find after release when we hit equilibrium, which means I need the first t value after t equals 0 when x equals 0. Okay, so x is equal to 0 corresponds to square root of 2 times sine of 4t plus 5 pi over 4 equaling 0. All right, well, square root of 2 is a positive number, so that means that is when sine is equal to 0. And remember, unit circle, sine is equal to 0 at exactly 2 spots when the angle is 0, when the angle is pi, and any other multiple thereof. So 0 corresponding to the coordinate 1, 0 on the unit circle, pi corresponding to the coordinate negative 1, 0, and then, of course, you could add 2 pi to either of those, and that gives you every integer multiple of pi. So 0, 3 pi, 5 pi, so on and so forth. 0, 2 pi, sorry, I was doing the other one. 0, 2 pi, 4 pi, and 0, negative 2 pi, negative 4 pi, all corresponding to when we're at 1, 0. Pi, negative pi, 3 pi, so on and so forth, corresponding to when we're at negative 1, 0 on the unit circle. So we can solve for t, but note that my solution depends on my integer n. So I didn't find a t yet. I've got a formula that tells me all of the possible t's that work. Note there are infinitely many. Okay, but I want the first t value after 0. So I want to start plugging in values for n, and I want the first n value that makes t positive. That's going to be the first time equilibrium is reached. Okay, so how do you figure this out? Well, you just look at it and plug in reasonable numbers. So, right, the first thing that I would do is I'd plug in 0, and I would get negative 5 pi over 16. All right, well, that's not after t equals 0, that's before t equals 0, so that doesn't work. Then I'll plug in 1, and then I'll note that, well, pi over 4 minus 5 pi over 16, well, 5 pi over 16 is bigger than 1/4, right, by a 16th, so that doesn't work. So that means that n equals 2, though, is when t goes positive finally, and thus the mass reaches equilibrium after release at 3 pi over 16. So that's the bottom line. Okay, so now note there are other values, but we wanted the first one. After release, when do we hit equilibrium? The first t value for which that occurs, in this case, 3 pi over 16. Okay. Now, we'd have a formula to generate all other future time values when that happens, but we wanted the first, and we got it. Okay, so now keep that number in mind. We hit equilibrium at 3 pi over 16 seconds. We now want to find the minimum displacement when we first hit that minimum displacement. Okay, now here by minimum displacement I mean the furthest away, minimally smallest number away from equilibrium, which we know is root 2. Negative root 2. Right, the amplitude of the motion is a square root of 2. Say negative root 2? Well, that's right, yeah. Square root of 2 is the amplitude, so the furthest away from equilibrium we ever get in absolute value is square root of 2. So we hit positive square root of 2, and we hit negative square root of 2. Negative square root of 2 is the minimum displacement, or if you think about the number line, it's the smallest, hence minimum. So I want to find the t value, first one after t equals 0, when x hits negative root 2. Alright, so that means we set x equal to negative root 2. That means sine of 4t plus 5 pi over 4 is equal to negative 1. So that means that 4t plus 5 pi over 4 has to equal 3 pi over 2. Note that's exactly the only time sine ever hits negative 1. Think about the unit circle, that's straight down when we're at x equals 0 and y equals negative 1. And, of course, any 2 pi multiple thereof. So if we rotate counterclockwise or clockwise a full length around, So that's what that is equal to. Okay. So again, we can solve for t. It's pi over 16 plus pi over 2 times n. Okay, so we plug in integers trying to find the n value that gives me the first time a positive t occurs. Okay, well, n equals -1, pi over 2 is bigger than pi over 16, so that goes negative. But at n equals 0, t is positive, so that is the first time we hit the t value we want. So then we conclude that the mass hit the minimum displacement at pi over 16. Now remember the setup of the problem, the wording. We took the mass above equilibrium and pushed it up above equilibrium. So we should hit the minimum displacement before we hit equilibrium, right? The mass was pushed above the equilibrium and then tossed upwards. It needs to hit the minimum displacement before it ever hits the equilibrium. Pi over 16 is smaller than 3 pi over 16, so our numbers line up with the physicality. All right, so our model sounding pretty good. Excellent. All right, there you go. Now that is, of course, is just a brief little sampling, a little taste, a little palate, a little amuse-bouche. That's what I was gonna say, palate cleanser. I'm like, that's not right. It's the other. What's the other pretentious thing I wanted? Yeah, amuse-bouche. Yeah. For how the mass springs world works. As I noted, we're just going to look at free and undamped. Of course, you could talk about damped motion, you could talk about driven motion, and right, you can even go well beyond that. Your book talks about like 2 springs attached. You can go nuts, but just gives us a nice little taste for how this exciting little slice of the math physics world works. So, all right, so that is it for that. Hope you liked it, and I'll see you next time.